Okay, let's get started. So today we're going to talk about strategy for your testing series. So we've learned all the methods that we need to determine whether or not a series converges, to determine what extent we can approximate the actual answer to what the series is by taking the first n terms, the partial sum of the series. And now we're going to put it all together, develop some kind of a strategy to determine which tool to use to answer these kind of questions, and then just practice it on a bunch of examples. So you remember when we learned integration, we had this whole collection, this whole toolbox of different methods, and then in the final section, we just had integrals and we just tried to do them with our toolbox. This is the equivalent thing. We have all our tools now, and now it should be the things you've learned, your intuition after practicing this, telling you which tool to use based on which series. And this is where it all comes together. So, just like with integration, there isn't just an algorithm I can tell you. I can't just say do step 1, step 2, step 3, step 4. You have to use your imagination, be a bit creative, use your intuition to know which tool to use. But you will quickly get good at this. You will quickly start to identify which is the right thing for the right situation. So I'm going to outline a basic kind of strategy you can think of as a way to start, but it's just a rough guide. You can figure out your own strategy, or you can use this or not use this as you like. But just to give you some outline, here's a potential way to do it. So, strategy for testing series. 1. Is it a p-series? Is it something of the form sum k equals 1 to infinity, 1 over n to the p? If so, then we know what's happening. So converges if p is bigger than 1 and not otherwise. Okay. Second thing, is it a geometric series? These are the two basic examples of series that we've been doing. Most of the series that we encounter are in one form or the other morally like a p-series or like a geometric series. And if it's a geometric series, as you know, it converges so long as the absolute value of r is less than 1. So it's the same as saying r is between -1 and 1. Okay. If it isn't directly either p-series or geometric series, perhaps it's like a p-series or geometric series. And if it's like a p-series or geometric series, then there are tools we can use. So the most precise tool we have is the limit comparison test, right? The limit comparison test is that if we see something that looks a lot like something that is either one of these guys, then we can try and marry it to one of these guys and see if we can actually marry it. If the limit of the terms of the series we're looking at, the ugly series, when we take the ratio of those terms with the terms of the attractive series, the one we think it is actually like, that ratio tends to some non-zero limit. If that's true, then we say they're married, and then the ugly series converges if and only if the beautiful series converges, right? So this like has a precise meaning for us. We learned about what we mean by like. Many cases, you don't need to bring out this tool. You can just see that the series you're looking at is a series of positive terms that is bounded above by something that is a geometric series or a p-series. And then you know it converges because it's bounded above by something that converges. Or conversely, you see that the series you're looking at is bounded below by either a p-series or a geometric series that doesn't converge. And therefore, you know it doesn't converge, right? So basically the series that we encounter converge either because they're like a geometric series or they're like a p-series. So this like covers a lot of stuff, covers a lot of territory. Okay, 4. It's not actually in the strategy, but I kind of also want to add this. Is it like a p-series or geometric series? Maybe it's a telescoping series. Four. Does the limit as n goes to infinity of these terms not equal to 0 or not exist? If that's the case, then for sure it doesn't converge, because that means the step sizes are not going down to 0. If we take this infinite collection of steps, we're never going to land in some place, in some particular point as we go to infinity. So if this happens, or the limit doesn't exist, then it doesn't converge. And this is the divergence test. Five, is it an alternating series? If it's a series like this, where these bk are positive, then we know it's going to converge if they're actually tending to 0 and they decrease. If they don't tend to 0, then for sure it doesn't converge by the thing above, but by the divergence test. If they tend to 0 and they are decreasing terms, then it converges. And the major point about this is that we don't care how quickly it goes to 0. So all the stuff we've been paying close attention to when we have just a series of positive terms, that's not true in an alternating series. This thing can go to 0 as slowly as you like, as we talked about when we kept drawing this picture and over again, right? Because we're just going forwards, backwards, forwards, backwards, forwards, backwards, and we end up trapped within an incredibly small area whose width is just depending on the bn+1 step size when we take n steps. Yeah? And therefore we see we're going to converge, and it doesn't matter how slowly these terms go down to 0. So that's the alternating test. Rule of thumb, if your series involves factorials, then the ratio test is a good thing to try. Because if it involves factorials, if it's going to converge, most likely it's going to converge more quickly than a geometric series, and therefore the ratio test will give us this fact. We'll have that the ratio of the absolute value of an+1 over an will tend to actually 0. All we need is that the ratio of an+1 over an to be less than 1. And if that happens, then we know it converges. The ratio test is this tool we discussed last time that allows you to detect if in its bones a series is like a geometric series, yeah, or going down to 0 even faster than a geometric series. So the ratio test is a good thing to do whenever you think what you're looking at is basically something that goes to 0, like or faster than the geometric series. So I'm just going to write seems like a geometric series. Geometric series. And I don't have space for the final couple of things. Okay, let's erase the board. So 7. If we see terms like this, b to the n to the n, then the root test is the natural thing to try. Can everybody who's here please put here in the chat? And finally, if none of those things give you an answer as to whether or not you think the thing converges, we can do the integral test. And we put this last because this actually does involve a calculation. We need to calculate an integral. So find f such that f of n is equal to an, and then series converges, or let me be more precise. So if f is decreasing, and these terms have to be positive, of course, if f is decreasing, and the integral 1 to infinity x dx exists, then I should say converges, then series converges. And otherwise, it doesn't converge. If this thing doesn't converge, if the improper integral of type 1 doesn't converge, then the series doesn't converge. And that's it. That's all the tools that we've learned. So this is a big enough toolbox to do all the things that you're going to encounter. Let's do some examples. Example 1. All right, let's launch into the examples. Let's do this. The sum from n equals 1 to infinity, n minus 1 over 2n plus 1. Okay. Look at this. Tell me what you think is going on here. Tell me if you think this is going to converge or otherwise. Let's take a survey. So everybody who thinks it's going to converge, put your thumbs up. Give me the thumbs up icon. And you think it's going to diverge, give me the thumbs down icon. Is there a series whose behavior we know that we can marry this thing to? How are you coming to this conclusion? Or if you don't think it converges, tell me something about that. Give me your reasoning. I need to know how you're thinking about this. What is the limit as n goes to infinity? Everybody else, is he right? Is the limit of these terms a half? Is that correct? Give me a thumbs up if you think that's correct. Everybody thinks that's correct, and it is correct, yeah? So notice that the limit as n goes to infinity for 2n plus 1 is just equal to 1 over 2, right? The dominant terms on the top is n, and the bottom it's 2n, so this is 1 over 2. Yeah? So these step sizes are getting closer and closer to just being a half. Yeah? So if we are the little man who represents this series, we're doing an infinite collection of steps of size basically a half. Yeah? Closer and closer to a half. And for sure, we are never going to stop, right? We are never going to stop. We're going to go all the way to infinity. Yeah? So it does not converge. By the divergence test. Yeah? Everybody see that? Give me a thumbs up if you're now happy with that. If you're not, then what I'd really like, if somebody has the courage to do this, is to tell me why you thought it does converge, so I can see what direction your thinking is going and try and set you in a different course. So does somebody have the courage to tell me why looking at this, you've got the impression it does converge? Or write it in the chat and someone else can write. If I get some idea how you're thinking, then that really helps me redirect you. Okay, cool. Thank you for that. I really appreciate you telling me that. All right, yeah. There are a lot of tests, and there are a lot of things in this mix. And this is why I want to emphasize all the time to not try and remember rules or remember symbols, but to think about the meaning of this thing, to turn this into pictures, to turn this into metaphor. Okay. So the metaphor I'm offering to you for a series is somebody taking this infinite collection of steps where each step is each individual term of the series. Yeah? And if you think about this, and you notice that as n goes to infinity is more like a half, then you're thinking about somebody who's taking a step of size a half going ever forward. Yeah? Yeah? And even if you're really mixing this up with the ratio test, your common sense says that if I'm just taking a step size a half forward all the time, then I'm just going to keep going forever, right? I'm never going to stop. I'm never going to stop. Yeah. So please try and make the stuff we're talking about be meaningful to you in terms of pictures, in terms of metaphor. Don't allow it just to be a rule that you remember. It's got to come off the board into some other form for you. It can't be just something you see on the board and remember. It's got to have some meaning for you, and that will really help a lot. Not just with this topic, but with all 5 topics. Okay, thank you very much again for telling me how you're thinking. All right, let's do another one. See how this goes. Let's do this. Example 2. What about this? This is 3n to the 3 plus n squared plus 2. Like this. Okay, same game, same deal. I want you to look at this and I want you to tell me if you think it converges or not. Thumbs up if you think it converges, thumbs down if you think it doesn't. Again, it doesn't matter if you get it wrong. It's really helpful for me to know where you are, where your thinking is. We're not keeping score. We're all together trying to help each other. So give me your feedback and don't worry about if it's wrong. It's almost helpful if it's wrong, because when it's wrong and I tell you what's the actual answer, it's going to be much clearer in your head. So don't be shy. Give me your feedback. Does it converge? Thumbs up if you think so. Excellent. So what you did was you didn't say this explicitly, but implicitly, what did you just do there? Even more, you did the, well, implicitly yes, but you did more than the comparison test. You used the better version, which is the, somebody help him? The limit comparison test. So what you did was exactly the limit comparison test, because you said, okay, this ugly guy, very complicated ugly guy, if I ignore the unimportant features, then I'm going to not pay attention to this one. I'm not going to pay attention to these lower terms. So I noticed that this expression is really a lot like, I'm going to put it, this is not an equal sign, this is an approximately equal, with the squiggle on the bottom. It's approximately equal to n to the 3 over 2 over 3 to the n to the 3. And that thing is just 1 over 3 n to the 3 over 2. Yeah, that's what you did. And what you're saying when you say this thing is like this thing, you're saying that if I try and marry this ugly guy to this beautiful guy, I'm probably going to succeed. And in fact, you will. If you take the limit of this thing divided by this thing, the limit will be 1. And that is exactly saying that they're very similar to each other in the sense of whether one converges, the other one definitely does converges. If one diverges, the other one definitely diverges. And this guy, for sure, we know it converges because by the p-test, since 3/2 is bigger than 1, this converges. Yeah? So what you were thinking was exactly right. But if we use the language of maths and we use this specific tool, then the way we would phrase it is, this ugly guy is marriageable to this beautiful guy, which we can express by taking this limit, the limit as n goes to infinity, of this guy, n to the 3 plus 1, over 3 n to the 3 plus 4 n squared plus 2, over 3 this, divided by 1. And if we factor out the stuff, if we factor out n to the 3 from inside the square root and factor out n to the 3 from the bottom here, and then we cancel this indeed will have limit just 1. So I'm going to skip the algebra, but check for yourself, or hopefully you can sort of see why this will work. Yeah? So they are married. So everything that this guy does, whatever it does, this guy also does. And this guy converges, so that guy converges. So you're right. Yeah? So for multiple choice, you'd have got that straight away. Correct answer. If it was a free response, you would do some extra things just to show the examiner that you know what you're talking about. You would calculate this limit. You would say, you would use what you would say by the limit comparison test. And then you get all the points. Cool. Everybody happy with this guy, with this question? Yeah? Excellent. Let me put a question up, and I'm going to ask you to think about it, and I will erase the board in the meantime. Let me do something a little bit more challenging. Okay. Look at this. This is question 24 from the end of the section. N sine of 1 over n. Write this down. Think about it. And when the board is erased, tell me if it's going to converge or not. This was our series. Thumbs up if you think it converges. Thumbs down otherwise. Why is it 1? Very good. Good. Yeah. Exactly. So Sine says we can write it like this, yeah? And as n goes to infinity, 1 over n goes to 0, and this is a standard limit, which we've learned, right? And even more, I hope you have this picture in mind that the sine function looks like this, right? This is what sine looks like, yeah? And if we take the tangent line to sine at 0, it looks like this, yeah? Because what's the tangent line to sine at 0? T of x is the derivative of sine at 0, which is cosine. Cosine at 0 is 1, yeah? So it's x minus, so the slope is 1, so it's x minus the point, which is the point is 0, so it's just x, plus sine at 0, which is 0, so the tangent line is just x. So this is the tangent line like this. Yeah? And if we look very, very closely down here, yeah, the way at which sine is going down to 0 is exactly more and more like the way that x is going down to 0, which is the same as saying this, that the limit as x over x, sorry, the limit of sine x over x equals 0. This is a basic limit that we should know, right? You see it from this picture, or you see it from this picture. We draw a circle we take this little angle here, theta. The angle's in radians, which means that the length of this part of the arc is exactly theta. Yeah. And then if we try and represent tan on this picture, if we try and represent sine theta on this picture, it's just this straight line like this, right? Because this is a circle of length 1. So we're comparing this straight line to this little bit of an arc, and we see that they both go down to 0, but the ratio of these two things going down to 0 will tend closer and closer to 1, because you can just see the lengths of them are more and more close to each other. Yeah. So this thing you should know. Yeah. And then just this rephrasing of this situation, this has to be the case that this limit is equal to 1. And hopefully that's how most of you came to the answer. Yeah? Most of you got this right. Cool. So by the divergence test, I'm going to abbreviate divergence to div. Diverges. Good. Let's do this one. This is example 3. What about this? The sum from n equals 1 to infinity, n e to the minus n squared. Thumbs up if you think it converges. Thumbs down if not. If we take the integral test, indeed. Yeah. We can take the integral test, but the integral test is a kind of a last resort because we actually have to do an integration. Yeah? But your reasoning is exactly right, that this guy is an exponential. He's even an exponential acting on n squared, so it's even growing faster. So it's going to beat out the polynomial term, which is just a linear term, quite dramatically. So it's going to go to 0 very fast. It's going to go to 0 very fast, and therefore we expect it to converge. Yeah, there we can expect to converge. We can check it with the integral test, or we can just mess around with it a little bit in the following way. So look at this. If we look at n squared for sure is bigger than 2n for n bigger than or equal to 2, right? That's true. Yeah. So therefore, e to the n squared is bigger than or equal to e to the 2n. That's also true. Yeah? So, n over e to the n squared is less than n over e to the 2n. Yeah, just from this. And what's that? That's n over e to the n times e to the n. And we know that e to the n is much bigger than just n. Yeah? Because exactly what you said, exponential kills the polynomial. Yeah. So this kicks in. I think it's true for every n bigger than 2 at least. So since, let's put it over here, n over e to the n is definitely less than 1 for n bigger than or equal to 2. Yeah. So this thing is less than 1 over e to the n, which is just 1 over e to the power n, which is a geometric series which converges. Yeah. So we could do some just messing around with these inequalities, doing some algebra, and we know for sure it converges. And this, if this was your free response answer, this would give you all the points because this is completely correct. There's no gaps in this. This is all there, yeah? So converges by the comparison test. Or we can just integrate it. So we can find a function such that f of n is equal to n e to the n squared. Such an f is obviously given by, well, maybe not obviously, but I hope you'll see that it's given by this. Yeah? So then our expression will converge if and only if this integral from 1 to infinity, this is this is actually more of a pain to do because we have to check that this is a decreasing function, so we have to take the derivative, check that it's negative, and then we'd have to calculate this thing. Yeah? But we can do that because we can do the u sub u equals x squared, and then it's going to be an integral we can calculate. But there's multiple steps in this, right? So, and check that f prime of x is less than 0 for all x less than whatever you want. With the integral test, with all of these things, we don't have to start at 1, we can start at 2, we can start at 3, we can start at 664, doesn't matter, yeah? For all x, but I think it's going to be true for all x bigger than 2, or whatever, just to make sure, bigger than 5, or whatever, or anything. So, if this is a free response, probably they'd expect you to do this, because you would maybe see the structure of this as something you can integrate by u sub. But you don't have to do it this way. This way, just comparing it in this way with this reasoning, this is completely valid too, and this is faster. And involves less calculation that you'll have the potential to get wrong. Is everybody with me here? I want to do this one. All right, maybe, yeah, okay. This is worth sticking around for. So watch this on video if you have to leave. Look at this. 2 to the k over k factorial. All right, thumbs up if you think it converges. Thumbs down if you think it doesn't. Okay. What was our series? It was k equals 1 to infinity. I guess 2 to the k over k factorial. So give me the feedback again. Thumbs up if you think it converges. All right, somebody who thinks this thing converges, tell me why. Perfect. Well, as n, yeah, you mean in general, so for general n, yeah, that reasoning is excellent. We have 2 times 2 times 2 times 2, n times, and on the bottom we have n, n minus 1, n minus 2, all the way down to 1. And in this example here, where you took 10, we have 10 terms, and we have 10 terms, and correctly point out the bottom is a lot bigger than the top, and as you correctly say, as n gets bigger, it's more pronounced. Yeah? It's more pronounced because these numbers, n compared to 2 is there's much more of a difference than 2 compared to 10. Yeah, yeah, and as n increases, it's more and more true. So yeah, it looks a lot like this thing will converge because we are completely winning this battle here of the denominator killing the numerator. And we can be a bit precise about it. So let's look at this. Let's look at this general expression. Let's cut off the first 2 terms. So we have 2 over n, and then 2 over n minus 1. And then let's put everything else here. So then we have 2 over n minus 2, 2 over n minus 3, and so on and so on and so on. We have 2 over 2, and then finally 2 over 1. Yeah? And all of these guys here are going to be less than 1, except for the final guy, which is equal to 2. Yeah? This guy is less than 1, this guy is less than 1, this guy is equal to 1, and the final guy is equal to 2. So the entire thing here in these brackets, in these blue brackets, yeah, this entire thing has to be less than 2. Yeah? Cool. So if this entire thing is less than 2, then this entire expression is just less than 2 times 2 times 2, which is 8, over n minus 1. Yeah? And now it's looking an awful lot like a p-series. Yeah? It's looking an awful lot like a p-series. It's looking like 8 over n squared. Yeah, and in fact, we don't need to do well, we could do the comparison test if you want, or we can just do this. This is less than, sorry, we can just do the limit comparison test, or we could just do this. This is less than 8 minus this over n squared. Yeah. And if we take the sum from n equals 2 to infinity, 2 over, 2, but 8 over n minus 2 squared. Let's not take it from 2, let's take it from 3. Oops, not 1, let's take it from 2, as I originally said. Like this. This is the same as the sum from n equals 1 to infinity, 8 over n squared, right? Because if we start from 2 and we go n minus 1, it's the same as starting from 1 and just going n squared, which converges. Yeah. And that's completely nailed down. There's no argument here. Yeah. This is absolutely without any no one can question your reasoning. Everything you've said is completely true. So if this was a free response question, you would get all the points. You'd have to get all the points because you have everything correct here, yeah? And you have the correct answer. Yeah? So that's excellent. That's very much the kind of thing I want you to do. If you don't think of this, then hopefully you will think, okay, this guy seems to be decreasing fast. Yeah, probably faster than the ratio test. Sorry, probably faster than a geometric series. Yeah? And therefore, a good tool to use would be the ratio test. And in fact, on the strategy, it says, when you see a factorial, consider using the ratio test. So if we do the ratio test, so we let ak be 2 to the k over k factorial. Then what happens? Let's look at this. These are all positive terms, so we don't have to put absolute values. So ak plus 1 over ak, what does it look like? 2k plus 1 over k plus 1 factorial. And the guy on the bottom is this guy, so we're dividing by this guy, which is the same as having k factorial over 2 to the k. There we go. Then what happens? Then the same stuff I was saying before. So what do we have from here? We just have 2, and this thing is k plus 1 times k factorial, so it's k plus 1 on the bottom here. And then the limit of this thing is actually 0. As k tends to infinity, ak plus 1 over ak is equal to 0. Which means that this thing converges. And what it says is that these terms are actually going to 0 faster than a geometric series. So this is really converging. And that does that. So 2 ways. I like the first way because it's elementary and you're thinking about what these things actually look like. I also like the second way because this, despite me getting it wrong, this isn't computationally particularly difficult, right? This isn't particularly difficult. You just need to know what k plus 1 factorial looks like. Yeah? Do some cancellations and then you see it. Yeah? So what would be excellent would be is if you have 2 reasons why you think something converges. And these are different reasons, right? I mean, it converges for the reason the series converges is the same, that it's going to 0 fast enough. But we have 2 different arguments why it converges to 0 fast enough. This argument here, we're comparing it to a p-series which converges to 0 fast enough. This thing is this machine of the ratio test, which tells us in its bones, this thing is going to 0 either like a geometric series or faster than a geometric series if the limit is 0, as in this case. Yeah? So you have 2 reasons why it converges, then you're absolutely sure. Cool. All right, everybody feeling happy with this? Everybody feels good. Okay, so we have a lot of time before the midterm. So we have time to practice this and get very good at it. And I claim that this isn't a difficult topic, might be new, but all of you who want to can really master this. You can get all of these questions right very easily and get all of these points. So please just nail this down. It won't take you that long to get very good at this, and you'll have a big chunk of the exam you'll have no problems with, and then we can focus on the harder topics and get those right as well. Okay. All right. So just practice this. You'll get good at it. Have a good weekend, and I will see you all on Monday.